Okay, guys, so let's talk a little about proving shapes are shapes on the coordinate plane. So this is a quiz that you're either going to be retaking or taking next time you come to class. So if you're here, you're trying to get some information to make sure you're doing it right. So the feedback I can give anybody is that what we saw is basically good stuff. But we had some formatting issues, and we also had some issues with formality, meaning I don't think people really understood the level of exactness you have to show us to meet the criterion for this proof. So anyway, I'm going to try to clear that up for you. So here's my intent. I'm going to go through these 5 homework problems with you, so you can kind of skip around as you need to. You're going to hear a very similar message on each one as far as the formatting and formality go. But you might, if you're confused by the content, of course, and you probably want to watch the whole thing. But take this as you will. So let's get into it. So on this first one, you notice a couple things. I already graphed all the points. I also labeled them. That's one mistake I saw. Like, not everyone was labeling their points, which made then proving this was, in this case, I think a parallelogram, pretty tough. And so one thing you want to do immediately when you have a problem like this is graph your points. Points are given at the bottom, and also label your points. So you're not talking about this line or that line. You're pointing and you're drawing arrows and stuff. Instead, you can actually properly label them. So that's job 1. Now, job 2 is to write something I'm going to call a statement of intent. So this is kind of like, if you remember, kind of like old school writing proofs. A statement of intent is the same thing as just kind of writing a proof statement. The point being, like, if you want to do this work well, you have to state exactly what you intend to show us and how you intend to do it, which means we have to think very carefully about the definition of this case, and we double check, of a parallelogram. So if you understand the definition of a parallelogram, that basically is your statement of intent. That is your proof statement. Let me give you an example of what I mean. And so if I'm going to prove ABCD is a parallelogram, then I have to meet the definition of parallelogram, in this case having 2 sets of parallel side lengths. So that's what I'm going to write. And you should write it. You should write it formally because it tells us that you know what you're actually trying to do. This is good for us as teachers because then we can see what you're trying to do. It's also good for you as students because then, if you mess up, we at least know that you knew what to do. You just messed up some kind of mechanical thing. So let's go ahead and write it. So, oh, I don't have a pen yet. Hold on. Okay. So way too big. Okay. So to prove, and the way you write this quadrilateral, you can just list the points. A, B, C, D is a parallelogram. Okay, and so to prove ABCD is a parallelogram, I will prove that there exists 2 pairs of parallel sides, and that's the exact definition. Now I'm going to actually name them here. AB, and let's make sure we're using proper notation. AB parallel to DC, and AD parallel to BC. Now this right here is actually still not good enough. Like, we were writing what we intend to show, but we never mentioned how we're going to show it. And so that's what's going to come next. So to prove ABCD is a parallelogram, I will prove that there exists 2 pairs of parallel sides, AB parallel to DC and AD parallel to BC, by comparing their slopes. Now, if I want to be super fancy-dancy, I'd add one more line here, showing that I know what I'm actually looking for. If the slopes are the same, then the lines are parallel. Okay, and I'm mixing notation as I go, but in the end, that's what I'm talking about. Like, that is a nice statement of intent. So even if I screw up the next part, even if I don't get the numbers to work out properly, I know I at least have a statement of intent. So I know I'm telling the reader that I know what I'm doing, right? Okay, I'm going to switch colors here. So now what we should probably do is go back in the diagram and actually make sure the slopes are going to work out as they are. So what you're going to see next isn't the proof. It's not formal enough, but it's work you're going to use to actually find the proof. Okay, there's a couple different ways we can do this. One is probably just by quickly counting. Like, we can kind of slope in our triangles right here. And so since I know slope is rise over run, I know that's running 1, 2, 3, 4, And so I know this slope is 1/4. Now, again, this isn't proof. This is just my work to make sure I'm on the right track. And I wanted to prove AB parallel to BC. And then up here, so we can, again, think of it kind of the rise over one triangles. So that's 1, 2, 3, 4. And so again, we see the slope here is 1/4. Okay. We can switch gears. Let's talk about the sides. We have 1, 2, 3, 4 over 1. So this slope's actually 4. And then my slope's 4 as well. And so I'm actually showing, or I'm actually kind of proving to myself, like, indeed, this is going to work out. The top and bottom lines both have a slope of 1/4, and the left and right lines both have a slope of 1/3. Now, again, this isn't good enough to actually meet the burden of the proof, but it's certainly going to help us out. It's going to tell us that we're confirmed, this is a parallelogram, I just have to prove it. And so, like, let's go ahead and go about the business of proving this. So, I should do a couple things. One, I should probably label, but also I should probably show some calculation. And so, like, a proper way to actually show this proof is not just by counting on a grid, but actually performing the calculation for slope. So a guiding principle for us is that slope itself is defined to be change in y over change in x. You guys probably know this as rise over run. But it's actually a formula. So the change in y is no different than like y2 minus y1. Just like the change literally is a subtraction problem. The change in x is the same thing, x2 minus x1. In other words, it's just going to be like the just a subtraction problem telling you how far apart they are. So the slope is actually going to be exactly that. Delta y over delta x, change in y over change in x, is y2 minus y1 over x2 minus x1. This is the calculation I have to show. So this is what we're expecting to see on either side for a nice formal explanation of why these slopes are the same. And so that's what I'm going to see on either side. I'll kind of split it up left and right. I'll try to label it the best I can too. So let's go ahead and make this side. Let's make this side for AB parallel to DC. And we'll make the side over here AD parallel to BC. And so I already told the reader that I'm intending to show the slopes are the same. So what I need to do is actually grab some points here. So let's drop this. Oops, drop that. Okay. So I'm going to kind of reference my diagram above. Since I already have everything nicely labeled, all I have to do is really just grab some values here. For AB, so I need A coordinates. So the A coordinate is 2, 3, 4, 5, 6. So negative 2 comma 6, which is right there. The B coordinate is 1, 2, 2, 3, 4, 5, 6, 7. So 2 comma 7. The C coordinate is positive 1, 1, 2, 3, so it's 1 comma 3. And the D coordinate is 1, 2, 3, negative 3 comma 2. Which if you look down at the bottom, those are all 4 listed, so we actually have them all good to go. Now I just have to calculate some slopes. So let's zoom in here. So the slope of AB, again, we're going to use this formula, y1 minus y2 equals over x2 minus, y2 minus y1 divided by x2 minus x1. So in other words, going from A to B, the delta y over delta x should be equal to, again, subtracting x numbers, 6 minus 7, and then subtracting the same x numbers, so negative 2 minus 2. Now we do have to do some simplifying here. 6 minus 7 is a negative 1. Negative 2 minus 2 is a negative 4, which just equals 1/4. So we have a slope of 1/4 for AB. Now let's go ahead and check DC. So going from D to C, delta y over delta x. D to C goes goes from 2 to 3, and then negative 3 to 1. 2 minus 3 on top is negative 1. Negative 3 minus 1 on bottom is negative 4. So that should just equal 1/4. And so right there, that proves that those are actually parallel because they have the same slopes. I could restate that if I wanted to, but I already stated it really nicely in my statement of intent, so I don't think I have to repeat it. Now let's go ahead and do this. Okay. So just for my convenience, I'm going to go ahead and copy and paste this list so I don't have to keep zooming in and out. So let's go ahead and find AD and BC. Let's go green. Well, actually, what color did I use? Red. Okay, let's go red. Okay, so AD and BC. So let's go AD. So again, we're dealing with delta y over delta x. AD, so A to D, we're going from 6 to 2. At the same time, the change in x would go from -2 to -3. And so let's simplify. 6 minus 2 is 4. -2 subtract off of -3 is actually a 1. And so that's just going to give us a slope of 4. Same thing, let's check BC. Delta y over delta x. Okay, from B to C, I'm going from 7 to 3. I'm going from 2 to 1. So 7 minus 3 is 4. 2 minus 1 is 1. That just equals 4. And again, just like before, my statement of 10 is pretty clear. So I don't really have to restate, like, this is why I know the parallel. But I've definitely met now my statement. I proved all of the 2 sets of lines of parallel. We're done. Now, to prove diagonals bisect each other, that's a whole kind of, I don't know, additional thing, I guess. So we have to kind of redraw that. So let's go back in our diagram. Let's kind of redraw our diagonals. And so I want to prove that they bisect one another. And now what that actually means is that they cut each other in half. And so I have to think about how I'm going to do that to prove they're cut in half. I have a couple options. One, maybe I can use a distance formula and try to work it that way. I don't think I'm going to try to do that in this particular case because, that means I have to know the point in the middle. And so that's not really going to help. I think instead I'm going to try to use the idea of midpoint. And so try to understand this point. If both pink lines bisect one another, then this point smack dab in the middle, the one I'm currently coloring in purple, that has to be the midpoint of both. If that purple line, which I'm going to call E, is a midpoint of AC and DB, the 2 diagonals, well then I would claim that has to mean that they bisect one another because they cross at a point that splits both in half. And so just like with the top one, I'm going to write a completely separate statement of intent for that. And so I'm going to do my work right here. Okay, so to prove so to prove the diagonals bisect each other, I have to show that E is a midpoint of, I'll go back up here, AC and BD by using the midpoint formula. Okay, so let's go ahead and do that then. Like, this is actually kind of straightforward because it is just a formula. I'm going to relay my points here. That's A, 2,7 is B, 1,3 is C, and that's D. So I can actually just show that formula right here. I don't have to do anything special. Let me give myself a little more room though. So the midpoint formula is defined to be x1 plus x2 divided by 2. That gives the x coordinate. Then y1 plus y2 divided by 2 gives you the y coordinate. Now, like before, I'm going to put this in the middle because I'm going to split up my work into 2 parts. Okay, so I had to prove that AC and BD use E as a midpoint, and so here's the AC work. So I have the coordinate points right here. There's A and C, and so the midpoint's defined to be -2 plus 1 over 2. That's for the x's, and then 6 plus 3 over 2. That's for the y's. I'm getting those directly from the coordinate points up here. And so the midpoint would be -2 minus 1 is -1, so that'd be -1 over 2. 6 plus 3 is 9, so that'd be 9 over 2. And so that's the midpoint I have to show. Also works out for BD, which I'll do right here. So the midpoint for B and D, and again I'm going to grab those points from right up here. There's D and there's B. So we have -3 plus 2 over 2, that's for the x's, and then 2 plus 7, and that's for the y. So now with some simplifying, -3 plus 2 is -1, so it'd be -1/2 again. 2 plus 7 is 9, so it'd be 9/2 again. And again, since I wrote a really nice statement of intent, I don't have to go and like re-explain my work. I already explained it right there, which is why that step's really important. Okay, so that was kind of long. I'm sorry about that, but that's what a full answer should look like. It should be comprehensive. And so going over the parts once again that you need a nicely well-used diagram, probably labeled with points and coordinates if you need them. If you're asked to prove something, I want you to write a really nice statement of intent, like this is what I want to prove. This is how I'm going to prove. This is what I'm being asked to prove. This is how I'm going to prove it. This is the mechanical, like formulaic thing that I'm going to use to prove it. Show me all your work. If you wrote a nice statement, you don't have to re-explain it. You just have to show it well. This work will require a calculation. So if you're trying to just kind of reason your way out of it, you're probably not going to receive full points because I asked you to prove it, not to explain it. And those two are very different things. On the additional one, you see this action again. They ask you to also prove that diagonals bisect each other. So to prove diagonals bisect each other, I have to write a nice little statement of intent. Again, I'm repeating the prompt. I'm showing you what I'm going to show and then how I'm going to show it. And then the work, formulaic driven, is at the bottom, okay? I'm going to do this, 4 more times for the rest of the homework. I hope that helped. I'll see you guys in a little bit in part 2.